Welcome to What That Means with Camille, where we take the confusion out of tech jargon and encourage more meaningful conversation about cybersecurity. Here is your host, Camille Morhart.
Welcome to Cybersecurity Inside. In this episode of What That Means, we are going to talk about intelligent systems today, and that's all in the context of artificial intelligence and augmenting human experience. I have with me today Lama Nachman, who is a fellow at Intel, and she's in charge of the relatively newly created Intelligent Systems Research Lab within Intel Labs. It's actually a combination of several other labs that have existed for a long time, so she's been doing research in this field for quite a while. We're going to ask her about what her lab does and what intelligent systems mean. This is actually part one. We have a part two where we speak with three of the people who work and run research projects within her lab and get into a little bit more detail about their topics. Welcome, Lama.
Thank you so much. I'm really happy to be here. So basically, we are a multidisciplinary lab that brings together social science, design, and AI, and hardware and software engineering. And what we're really trying to do is figure out how do you augment and amplify human capabilities and experiences with AI. So we use a social science-based approach to go and understand what are all of these unmet needs in the world, and then go and understand what type of innovation that needs to happen on the AI side to actually bring major improvement in these life experiences for people. So that's at kind of like the experience level and a lot of the human AI collaboration pieces of that puzzle. We also do a lot of innovation at the lower level on the algorithmic side to really try to, in some sense, solve some of these hard problems that are essentially today standing in the way of scaling AI in real world applications. And those range from how do you improve accuracy? How does it learn in new environments that it hadn't seen before? How do you actually do inference at like extremely large scale? Learn from very limited data, and then also try to get to things like explainability and usability of these systems.
Lama, can you tell us also what research you personally have been focused on over the last couple of decades, I guess, really?
And so I came to Intel in 2003, so about 18 years ago, I guess now. My work actually started in wireless sensor networks and trying to essentially connect the physical world and the digital world. So a lot of sensing and understanding from all of these different sensed data to try to actually change the way that we do work in different things. We moved towards trying to sense people and applied a lot of that towards health applications. So things like pre-diabetes monitoring as an example. And then we moved on to really try to scale to just understanding context in general so that we can make technology more aware of the needs of the user. And that started with a lot of on-body sensing. So we've done a lot of work where, wearables and things like that. And then we expanded towards just understanding essentially everything that's happening in the environment around you. So the whole notion is that if technology is able to really understand people and what they're trying to do in the world, not necessarily just from interacting with the PC or interacting with the phone, but actually what you're trying to accomplish in your everyday today life, right? In terms of learning in a physical environment or working in a fab or, just helping people with disabilities as an example, what can we utilize as signals in the physical world? And then with a lot of algorithmic innovation, turn that into understanding so that we can better facilitate experiences for people as they traverse their normal life.
Is this getting smaller and smaller, like from on-body to in-body? Are we seeing a trajectory in that direction?
So we see smaller and smaller, and we see bigger and bigger. So actually we see traversal in both of these spaces. Definitely sensing has gotten smaller. Computation has gotten much more efficient so that we're able to actually materialize systems in tiny implementations. But also, if you think about it, it is spreading into the environment in ways that we have not seen before, which is actually, if you think about it in terms of data, it's translating to just an unbelievable amount of data. We started by saying that this lab is actually part of Intel Labs. And, beyond just ISR, if you think about Intel Labs as a whole, that's really what we're trying to conquer, right? Which is how do you essentially get to capture data more effectively, process it more effectively, move it, store it, because everything is really is being changed by that explosion of data.
You're looking at, I think, augmenting the, I guess, human experience. So we're focused on humans here, and using technology and using sensors to understand better what the human is experiencing and then improve that experience. Is that kind of the high level?
There's a lot of work that you can think about in terms of just how do you improve the experience with technology, as in, I'm using my PC and I can make that experience better. And in some cases we do that, right? Because the PC ends up being, for example, maybe the conduit of communication, like right now, right? You and I are communicating. One of the things that we know people struggled with throughout the pandemic is that what we call the Zoom fatigue, right? Or any telepresence fatigue. And that's because trying to bring that back to the communication is not something that actually makes sense. And people use all of these subtle cues, and actually better representation of the physical world is much better to enable that type of communication. So in that specific case, maybe you can think about it as it's enhancing that experience, right? That's facilitated by the technology. But if you think more broadly, when you step into a manufacturing setting and you have a technician who's actually working on some equipment in the fab, right? And they're trying to fix something or transition from one task to another to print a totally different processor or something like that, they do a lot of these tasks in the physical environment. And we also think of technology, and a lot of the work that we do is really bringing technology to understand what people are doing in the physical environment and then assist them. So if you understood what somebody's doing, and if you understood what is supposed to happen, and you can actually converse, like the AI system can converse well with the human, then you could see how you can start to think of these things as human AI systems, where we're bringing the best of the human and the best of the AI system without getting stuck at what's not good about either one of those. So we're trying to really leverage the diversity in human AI systems to say, people are good at some things that AI is terrible at, and vice versa. So how do you, rather than get into this, we're trying to replicate humans, how do you get into this place where you can actually make AI systems much more resilient, make them shine in the things that they really do well, which is processing massive data and finding patterns in massive data, but humans are not really good at that. But they're very good at learning from limited data in totally ambiguous situations that they have never seen before. And if you actually bring those two things to the table together, you actually have a much better outcome.
You were making a comment about humans being particularly good at learning in brand new situations.
And AI systems struggle with that all day long, because they really need to see tons of data and train on that data. There's a lot of algorithmic innovation to try to look at how do you do, minimal data learning, zero-shot learning, all sorts of things like that. But ultimately, if you think about what humans are really good at and doing at very, very low power, that's not looking through trillion of data points from the fab and trying to figure out what's wrong. It's actually looking at the very, very totally new setting, something that they've never seen before, and be able to actually connect the dots in that. So that's something that humans are very good at, machines are terrible at. And the other example is like humans are really terrible at, machines are good at. And both of these things are usually needed to solve any problem in the real world.
So give us an example of something, and it can be far-fetched and it can be hypothetical and maybe not, we don't even know if it's going to happen, but what sort of thing might you imagine this could enable in the future? What kind of a use case or scenario?
Maybe give you a couple of examples that we've been working on. So one is, I kind of alluded to that in manufacturing settings. It's amazing because we've done tons of automation in general, especially in chip manufacturing, right? I mean, you walk into fabs and many of the things that used to be touched by hand, especially to actually have less contamination and things like that, they're actually automated in the way that we move wafers and things like that. But you walk into a fab and you still see tons of people. It's not like people disappear. They just do different tasks in the fab, right? So now one of the things that I mentioned, which tends to be a problem, is that you typically, these type of tasks have very specific set of specs associated with them. So you could imagine having an AI system that can ingest all of these specs through natural language processing and understand that these are, the different tasks that someone should be doing to actually perform this specific procedure. And you have people clearly doing that and pursuing that. Now you could train, and this is what we're working on, is training essentially an AI system to recognize the specific tasks and subtasks, and these things are long, to actually aid people in figuring out what information they need in the moment, what specific next tasks. So sometimes people forget things. And then you can remind them, you can highlight that, look, this isn't actually cleaned, and you just skip that step. And those are things that if the AI system can take all of this natural language processing and bring in the looking through the camera to understand physical tasks that people can do and make that link, it can then massively bring a lot of information, including information that it has seen across multiple users. So to enable human to human learning. Because what you see in these settings is that you have people who have done this and they're experts, and you have novice and they don't know these things. And sometimes experts skip things for a reason. So having that ability to dialogue with the person and highlight these things and have actually the person help the AI system in its learning. It's like, okay, no, it made a mistake in recognizing this thing. And the person can say, no, actually, this is X, right? And then the AI system continue to learn. So now you're bringing in some of the knowledge of the human, especially the experts, and helping train the AI system in what should happen. And you're actually enabling the AI system to support the novice, or sometimes somebody who's just even an expert who sometimes will leave something in a machine that they should have not left, for example, as an example, because people do make errors as well. So there, you can't really just go and say, I'm going to get tons of data and I'm going to train this system on this one procedure. And then the next time the procedure change, which happens all the time, I'm going to have to go start from scratch again. You can't do that because that's not scalable. But if you actually figure out how to get the human to teach the AI system as they're going, and to have the AI system help the human when they make mistakes, or like what was this other thing that I needed to do, and bring that information, so you can actually enable that conversation to happen, and then you will have a much better outcome. Another example that we've been working on quite a bit is actually in early childhood learning. And there, one of the bigger issues that we see is that we've done a lot of ethnographic research that pointed to parents, on one hand, they really want to bring the best that technology can bring to their child's education because they see the benefit of that. But they're extremely worried about screen time, and rightfully so, because we've seen a lot of research on how that is actually translating to a lot of issues in the longer term. So then if you actually step back and think about it, how does learning happen actually in early childhood learning? If you walk into a kindergarten class, you don't see people actually on laptops and tablets. You see them on the floor, on the rug, playing with manipulatives, learning math by putting objects together. All these type of things happen in an actual classroom environment. So one of the questions that we were asking is, how can you get an AI system to actually observe what's happening in the room and be kind of a peer learner? Because actually the AI system isn't going to figure everything out. But if it can help a student, for example, in math learning, it can actually watch as they're putting these blocks together and exercising a lot of these things that they were taught in the class. And now they have to practice and do all of these things. So maybe they're putting blocks and rods together. They're mapping to tens and ones and additions and subtraction and comparisons and things like that. But they're doing that in the physical world. So that means the technology needs to come into the physical world, observe them, and then have a conversation with them that is actually situated in that physical world. Because that's what it needs to be able to do. I need to be able to understand what action you've taken and comment on it, and then analyze whether you've done that right or not. When you start pointing, I need to understand what you're pointing at. And kids, I don't know if you've seen kids interact. They don't interact the way we interact with Alexa. You'll see them going, like literally in a lot of the studies that we've done with kids, they'll be going like,
right.
I'm like, okay, that is an interaction that you actually need to be able to actually perceive and understand.
Okay, and that's maybe like gesture recognition, and it's different in kids and adults, but where is this AI going to sit? It's interpreting natural language. It's maybe interpreting video or gesture or different cues that humans give. Like, where is it? Are we talking the great eye in the sky now, wherever we are?
Ultimately, what you're really trying to do is bring engagement. Because what we know from pedagogy research, that learning outcomes correlate with engagement of students. So to try to get this to be an engaging environment, we've actually gone all the way out, right? So this thing actually projects this peer learner. He's aware of the physical space. He's a teddy bear-like thing that jumps all over things that kids can help him, build structures for him so that he can traverses it. And because of the fact that we're able to map the environment, we will understand there's a box that somebody put in that Oscar can jump on and land on and still obey the laws of physics. But it becomes kind of this digital physical world connection that makes it much more engaging.
Is this actually a robot? I don't know that I understand.
It's actually projected. It's actually projected in a projection space, but we're able to actually map out the physical environment. Now imagine you have this thing on the wall that's actually moving, and then there is like a box that the kids have put up, and then he can jump and land on that box. Mm-hmm. So you're actually almost like bringing him out of the wall of the projection onto that physical. So it becomes much more engaging. And we've done actually deployments in the school where, we could actually see a very different level of engagement because of the fact that now they're engaging with Oscar as if it's actually a physical thing in that world, even though it's not actually embodied. But to answer your question about then where does it live? So in that case, just imagine, right? You have a huge wall with projected everything. You have LiDARs, you have 5 cameras in the environment, things like that. This is really turning a space into a smart space. So now you have a server running in the school that's actually doing that. That is great if you're actually trying to understand what is the unlimited version of that. But one of the things that we've done, especially when COVID hit, because this project actually started pre-COVID, and then COVID hit right in the middle of this project. So we had managed to get one deployment in a school in Hillsborough before that happened, and that gave us a lot of insight. But then we turned around and we said, what is a minimal viable thing of that experience that you can actually deploy in people's homes? That would be something that we'd always need as well. So then what we turned towards is trying to bring that Oscar character and have not a huge physical environment, but think about a rug on the floor with a laptop that facilitates that sensing and computation and all of that stuff. So you're essentially still creating a smart environment because the kids are sitting on the rug and playing with these manipulatives, but it's actually enabled by essentially a laptop and a couple of peripherals. And that all clearly one of the things that are very important for us, things like privacy and so on. So we make sure that all of that processing is actually happening at the front end and so on and so forth.
So this is like taking the digital world and using it to enhance the real world. And I can't help but be thinking about right now all the conversation around Metaverse, which is basically moving people into the digital world, or the concept is that. And how would this kind of technology play out or become a catalyst for something like that?
If you talk about Metaverse, and it's funny because I've talked to multiple people, multiple friends that I have at Facebook and other places and whatever, and everyone has their own interpretation, by the way, about Metaverse. So sometimes we talk about it as if it's a known thing.
Well, maybe you should actually define it quickly.
In one high-level interpretation of that, it's really about everything becoming ubiquitous. So then you're actually connecting the physical world and the digital world in some interesting ways. You actually interpret things differently. You have all sorts of different devices that have to live within that makes these type of experiences possible. But I want to just kind of step back for a second and say, ultimately, there are all sorts of experiences within that spectrum, all from total virtual reality, where everything is virtual, to everything analog, and everything in between within that spectrum. So to me, what's really interesting about this is, what is the problem that you're trying to solve? And what are the concerns that you have that you're trying to mitigate? When it comes to early childhood learning, what we've heard time and time again from parents is that they really want this to be as analog as possible, with intelligence just enabling or bridging the gap of where the analog equivalent is not possible. So if you were to have a teacher for every child in the world, that would be fascinating, but that's not reality. So then the question is, how do you not then turn that into the other extreme, which is now everything is virtual? Like if everything is virtual, it simplifies how you consume content, how you deal with it. But if you start to say, well, no, I just still want the physicality of the physical environment, but I want actually the intelligence to comprehend that, it's a much harder problem. Because if I put you in the computer, it's much easier for me to actually do everything and observe everything that you do. And I think that is really the struggle, because in some things, totally virtual is absolutely fantastic, especially if you're enabling things like, I want to do remote health work. That's fantastic. It works out really nicely and it does everything that you need. But we have to understand that there are very different experiences within that spectrum that needs to be enabled. And technology needs to come in as a way to understand where it plays and where it doesn't.
Can you just talk about what are the different kinds of things via wearable or via video or via whatever sensors you're using to actually get a sense of the environment?
We essentially utilize visual input. So camera, whether images or video that you're talking about. And these things are very different, right? Because sometimes what you're trying to do is get to fine action recognition, and you really need a lot of the details. And sometimes you're trying to understand activity, like a kid is actually jumping up and down and doing these type of things. And you can do that from like a distance and more coarse and skeleton type interactions. We do a lot of work with audio, and with audio, I mean both understanding background audio and what's happening in the background. So like the scene of the environment, if you will, the audio scene, and that provides a lot of context. So what you're hearing in the background, and then what you're hearing in the foreground, which is actually the speech. We do a lot of work with text. We do a lot of work with physiology. A lot of the things that have to do with emotion and engagement and things like that actually have a physiological component to it. So if you're able to detect things like heart rate and skin conductance, that gives you a lot of input. We also do a lot of work on BCI. So we get EEG signals as well, especially for people with needs for accessibility.
What is DCI?
BCI is brain-computer interface. You essentially wear a headset, right, that has electrodes. And then what we could do is capture essentially EEG or brain waves to enable people to communicate with the PC because they can't move any other muscle. So this is, imagine someone who's totally locked in, like someone with ALS that can't move any other muscle. We also have been doing a lot of interesting work in using Wi-Fi as a sensor. And that might not be obvious because we think of Wi-Fi as a method for communication. But if you think about it, specifically when you get to the issue of privacy, we actually, when we move around in the physical environment, we disrupt Wi-Fi signals and wireless signals generally. So we've been trying to utilize that disruption instead of being a noise on communication, being the signal in human activity. So we try to essentially take that data and turn it with machine learning algorithms to understand people's activities, what they're actually doing in the physical environment. The cool thing about this is that from some of the ethnographic research that we've done with elderly people in their homes, they have a major concern about having a camera watching them, even though they're willing to have a system that can understand that they're doing fine and they're progressing usually with their day-to-day activities, because then they can stay longer in their homes. They're fine with that inference, but they just don't want a camera because they're worried about somebody seeing them in settings and whatever. So then what we try to ask the question is, well, if you actually, to solve some of the privacy issues, one of the things that you could do is reduce the gap between what is being sensed and what's being inferred. So with wireless sensing, you're actually pretty much sensing what you can infer. You don't have all of this high resolution images and things like that to then infer that somebody just went to the kitchen to do something.
I guess without getting into too much detail, like how much can you tell about a person from their interference with a Wi-Fi signal? Are we talking about just where they're located, or are there other kinds of reaction?
Now, if you can detect motion, you can start to look at what type of motion maps to what activity. So one of the things actually that we've done, which is really not what I just mentioned in terms of activities of daily living, but one simple thing that you can detect is if somebody's actually walking towards their PC to turn it on. And then you can start turning things on in the background to make it more timely, right? To get to it once you get to it. But, you can understand that somebody is actually walking around in the kitchen. You can over time start to understand this looks like somebody's actually preparing dinner or something like that. Another area that we've been focused on is actually getting physiological signals. So you can detect breathing from wireless signals, because essentially what's happening is that your chest is moving. On one hand, you could argue that movement is much smaller, so it's harder to detect. On the other hand, it's much more periodic. So in some sense, there is something easier about detecting something like that. So we have some POCs that are showing detecting actually breathing.
Could you determine then like how many people are present from something like that?
That's another thing that we're actually trying to do. And there are things that you could do by actually almost piggybacking on the breathing thing. Usually you can detect presence by movement.
Right. How much can we tell about thoughts? You were talking about patients with ALS or people who can't move at all, even to signal yes or no. And I know a long time ago, it was kind of like we could tell people to picture playing tennis or picture walking around their room. And one meant yes and one meant no. And therefore we could communicate with people that we had considered vegetables. And it's come a long way. So can you tell us how far it's come?
Maybe I would separate that into a couple of areas. The thing I was really referring to is active communication, not necessarily understanding thought. Like if you have the intention of doing something, and really the way it works is just imagine, let's say you have a lot of different options on the screen, or maybe a keyboard, right? And you flash different things on the keyboard. If you're intending to type a specific letter, when that letter flashes, we know that there is a different signal that comes out in the EEG signal that we can tap into. It's very noisy. It's not very clear, especially that this is not embedded in your brain. This is just a cap that we are wearing, right? Mm-hmm. So that makes the fidelity of the signal much less. So then if you do that, then basically what you're able to do is with multiple repetitions to reduce the error, and we're bringing language models into the picture, then you can start to guess, oh, this person meant to type this letter. In some sense, what you're doing there isn't a controlled thing. Because when you're trying to interact, I give you a keyboard, I'm going to flash things in a way that I can make my detection easier, because ultimately the goal is actually communication, as opposed to just kind of more generally trying to understand thought that's actually more implicit in nature.
Free-flowing or unstructured data. But if you couple that with the physiological reactions, it seems you could get a lot closer. Interesting.
Is frankly a game changer if we can figure it out. And a lot of people are working on this problem, is trying to understand emotion. Emotion is like a wide area, and you could argue all these things that I just talked about, which is engagement, for example, in school setting is an important piece because it enables, we've done a lot of work to try to help teachers understand how engaged students are. And you can get some of that from camera and content from the content platform and things like that. But one of the things that we've realized as we've put some of these things out to test out in the real world is that if the machine can actually help the teacher understand where kids are engaged and when they're not, then it can actually, what we've seen as we deployed this in real classroom environment in classes with and without that technology, is that more of the time then ends up getting spent by the teacher helping confused students, as opposed to start trying to go around and figure out who's engaged and who's not. If you empower the teacher with some of this information, the teacher is able to actually do, her job or his job better because of that actually empowerment, right? And engagement there, you could think of engagement as being, one example of that emotion spectrum. You can think of that as I'm putting technology in, and as I start to do things, if I'm really pissing you off, I should be able to understand that. I mean, I don't know how many people scream at their digital assistant all the time. I do this all the time with the hope that it would understand not to do this to me next time. It's a signal that's important if you're trying to make intelligent systems learn in the real world.
The final question for you is, obviously we've come close to talking about a lot of things that would, I imagine, bring up privacy concerns for people, ethics concerns. So can you just let us know what your lab is thinking about with respect to this, or how you can take in considerations?
One of the really good things about looking at this from a multidisciplinary perspective is that much earlier in this cycle, and it's actually something that we've been doing across all of Intel, which is how do you enable responsible development of AI? And that means at the very, very early stages, you're asking questions about risk. And you're looking at the project as a whole, even before you start developing. Because if you think about ethical concerns happen at different stages. There are ethical concerns with what a system does and whether it should do this in the first place, which is really kind of what we try to flesh out early on. And then there are ethical concerns about, is the thing that I developed in the way that I've developed it starting to bring ethical concerns? So the example that I talked about with wireless, for example, versus camera is one about the development. There are different methods of sensing that reduce privacy risk, as an example. How do we infer as close to the sensing as possible so that data is reduced and you're not sending raw data back, actually then makes the privacy concern more. We're trying to understand, how do you actually bring the human capability into this picture, rather than assume that the only way that you can actually bring AI and innovation is to replace humans? How do you bring better outcomes and really shared prosperity when you think about the key role that humans play into the puzzle? We look a lot at equity, right? And a lot of the work that we do with accessibility is really rooted at how do we bring equitable outcomes despite the range of abilities and capabilities that people have? So that's a big part of what we do. And then, of course, looking at bias in a lot of the algorithms that we build and ensuring that we're not just replaying the bias that's in the data in the world come back at us through the AI systems that we build. So those are some examples. It's really just something that permutates through everything that we do within the lab.
I have to just say a word and just get your reaction to it. Machine consciousness.
That actually is going to take me half an hour or an hour to actually even touch on. I think there are very different ways of thinking about what that means. It becomes very clear to me when we're talking actually about disability and creating systems that help support people in essentially being almost a representation of people who can't actually communicate for themselves. And that's the extreme case maybe that becomes kind of more obvious, where there's a meaning into that. And to me, in that case, it's really about machine consciousness really mapping towards what the human consciousness is and what people are really trying to do and accomplish with their life. You could go all the way to the other end of that spectrum and say, okay, well, now if we're talking about these intelligent systems and what consciousness of their own do we want to think about and do we want to bring? And that, frankly, I can't do justice in a minute of a conversation.
Okay, I'm going to pull you in then for another conversation if you're up for it. I would love to talk about it. Lama Nachman, Intel Fellow, running the Intelligent Systems Research Lab within Intel Labs. Fabulous conversation. And in a part 2, we're going to talk with several members of your team and dive a little deeper into the specific kinds of research that they're looking at within your lab. Thanks for joining us.
Never miss an episode of What That Means with Camille by following us here on YouTube. You can also find episodes wherever you get your podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.